Hello friends, in this video we will see algebra of sequences of real numbers. Means how to take addition, subtraction, multiplication, division of two sequences of real numbers and how to multiply a sequence of real number by scalar. Okay. Let xn and yn be sequences of real numbers. Then how to take addition of these two sequences. Addition of sequences xn and yn is denoted by xn plus sequence yn, and it is defined as addition of these two sequences is a sequence whose nth term is xn plus yn. Subtraction. Subtraction of sequences xn and yn is denoted by this, and it is nothing but xn minus yn. Sequence whose nth term is xn minus yn. Third, multiplication of sequences xn and yn is denoted by xn dot yn, and it is defined as xn dot yn. Means nth term of the sequence is xn, the multiplication of xn and yn. Fourth, division. Division of sequences xn and yn is denoted by this symbol, and it is defined as sequence whose nth term is xn divided by yn, provided yn is not equal to 0 for all n belongs to n. Fifth, scalar multiplication. Let alpha is a scalar, then the scalar multiplication of suppose alpha and xn is denoted by this symbol alpha into sequence xn, and it is defined as a sequence whose nth term is alpha xn. Let's see all these operations by example. Let sequence xn is equal to suppose a sequence whose nth term is 1 by n, means it is equal to suppose this is sequence whose first term is 1, second 1 by 2, third 1 by 3, fourth 1 by 4, and so on. And let's take another sequence yn is equal to a sequence whose nth term is n plus 1 upon n, means it is a sequence whose first term is 2, second term 3 by 2, third term 4 by 3, fourth term 5 by 4, and so on. Then addition of these two sequences, xn and yn is a sequence whose first term is 1 plus 2, 3. 1 by 2, second term is 1 by 2 plus 3 by 2, that is 4 by 2, means 2. Third term is 1 plus 4 by 3, 5 by 3. Next term is 6 by 4, we can write it as 3 by 2, and so on. You can say that his nth term is, this is sequence xn plus yn, and this is equal to 1 by n plus 1 by n, and that is sequence n plus 2 by n. Now subtraction of sequence yn from sequence xn is a sequence whose first term is 1 minus 2 minus 1, 1 by 2 minus 3 by 2, that is minus 2 by 2 minus 1, next 1 by 3 minus 4 by 3 minus 3 by 3 minus 1, and you can observe that next term is also minus 1 because it is xn minus yn, that is sequence nth term is 1 by n minus n plus 1 by n, and you can note that this subtraction is nothing but minus 1, means this is constant sequence minus 1 whose each term is minus 1. Next, multiplication xn into sequence yn. This is sequence whose nth term, first term is 1 into 2, 2, second term is 3 by 4, 1 by 2 into 3 by 2, third term is 1 by 3 into 4 by 3, that is 4 by 9. Next term is 1 by 4 into 5 by 4, that is 5 by 16, and so on. And this is xn into yn. Now what is xn into yn? 1 by n into 1 plus 1, n plus 1 by n, and that is a sequence whose nth term is n plus 1 by n square. Now since sequence yn is non-zero, here division of these two sequences is defined, that is xn by yn, and this is equal to a sequence whose first term is 1 by 2 next term is 1 by 3, 1 by 2 divided by 3 by 2, 1 by 2 will cancel, remains 1 by 3. Third term is 1 by 3 divided by 4 by 3, that is 1 by 4. Next term is 1 by 5, and so on. This is sequence whose nth term is xn by yn. That means here xn is 1 by n, yn is n plus 1 by n, and you can note that 1 by n, 1 by l will cancel and remains 1 upon n plus 1. Okay. Let instead of alpha, suppose if you take okay, if you multiply sequence xn by suppose 2, then what is 2 into scalar multiplication of 2 and sequence xn, that is equal to, means we have to multiply each term of the sequence xn by 2. We will get a sequence whose first term is 2, second term 1, third 2 by 3, next is 1 by 2, and so on. And this is a sequence whose nth term is 2 into xn, and that is 2 into 1 by n, and it is sequence whose nth term is 2 by n. Okay. Let's see algebra of convergent sequences of real numbers. Let xn and yn be convergent sequences of real numbers converges to P and Q respectively. Then the addition of sequences xn and yn, that is sequence xn plus yn converges to a real number P plus Q. Let's see its proof. Given sequences xn and yn converge to real numbers P and Q respectively. And we claim that the sequence xn plus yn converges to P plus Q. Okay. Let epsilon greater than 0 be given, be any given positive real number. See, to prove this, we have to find a natural number n node such that mod of xn plus yn minus P plus Q is less than epsilon for all n greater equal n node. Okay. Let's find this natural number n node using given data. We have sequence xn converges to a real number p. Therefore, for first we'll see first we'll do one adjustment. So consider xn plus yn minus P plus Q. See, we can write this term as by doing rearranging the terms, we can write it as xn minus p plus yn minus q, and by triangle inequality we can write right hand side as mod of xn minus p plus mod of yn minus q, and note that it is true for each natural number. This is also true for each natural number. Means now we have mod of xn plus yn minus p plus q is less equal to mod of xn minus p plus mod of yn minus q, and it is true for all natural number n. Okay, let's call this as 1. See, we have sequence xn converges to a real number p. Since epsilon is positive, epsilon by 2 is also positive. So for epsilon by 2 greater than 0, there exists a natural number n1 such that mod of xn minus p is less than epsilon for all n greater or equal n1. Similarly, we have sequence yn converges to q. Therefore, for epsilon by 2 greater than 0, sorry, there should be epsilon by 2. For epsilon by 2 greater than 0, there exists a natural number n2 such that mod of yn minus q is less than epsilon by 2 for all n greater or equal n2. Okay. Okay. Now take a natural number n naught which is maximum along n1 and n2. Note that n1 and n2 are natural numbers, so maximum of n1 and n2 is also a natural number, and you can say that since n naught is maximum of n1 n2, n naught is greater or equal n1 and n2. Okay, if n is greater or equal n naught, then we can observe that n is also greater or equal n1 and n2. This is because of law of trichotomy. Means n is greater or equal n naught is greater or equal n1, so n is greater or equal n1. Similarly, n is greater or equal n naught is greater or equal n2, n will be greater or equal n2. But for n greater or equal n1, we have mod of xn minus p is less than epsilon by 2, and for n greater or equal n2, we have mod of yn minus q is less than epsilon by 2. Let's take addition of left hand sides. Mod of yn minus p is plus mod of yn minus q, and note that addition of left hand sides is strictly less than addition of right hand sides, epsilon by 2, epsilon by 2. Okay, and it implies from 1 right hand from 1 we can see that left hand side of this term is greater than mod of xn plus yn minus p plus q, means we can write that from 1 mod of xn plus yn minus p plus q is less than epsilon by 2 plus epsilon by 2, that is less than epsilon. Yes, means we have proved that for any given epsilon greater than 0, there exists a natural number n naught. There exists this natural number n naught such that mod of xn plus yn minus p plus q is less than epsilon for all n greater equal n naught, and hence sequence xn plus yn converges to a real number p plus q. This is the end of the proof. Okay. Let's prove. Theorem. Let xn be a convergent sequence of real numbers converges to p and alpha is any real number, then the scalar multiplication of alpha and xn is a sequence obtaining from multiplying each term of the sequence xn by a scalar alpha. Then this sequence alpha xn converges to a multiplication of real numbers alpha and p. Let's do it. Given xn, the sequence converges to a real number p and alpha is a real number. Okay. We claim that the sequence alpha into xn converges to a real number alpha into p. Okay. Let epsilon greater than 0 be any given positive real number. See, to prove the claim, we have to find a natural number n naught such that mod of alpha xn minus alpha into p is less than epsilon for all n greater equal n naught. Okay. We divide this proof into two cases. If alpha is equal to 0, if case 1, if alpha equal to 0, then the sequence alpha xn is a sequence whose terms are 0 0 means it is a constant sequence, and it converges to it converges to 0, and we can write 0 as alpha into p if alpha is 0. See, if alpha is 0, then alpha into xn is 0, alpha into p is 0, mod of 0 minus 0 is mod of 0, and that is less than epsilon, because epsilon is positive, means the result holds. For alpha equal to 0, the result holds. Okay. Now, suppose alpha is non-zero, then mod of alpha is greater than 0. Okay. See, mod of for alpha non-zero, mod of alpha greater than 0. Okay. So consider mod of alpha into xn minus alpha into p. We can write this term, from both terms we can take alpha common and remains alpha into xn minus p, and by separating mod we'll write mod of alpha into mod of xn minus p, and note that it is true for any natural number n. Okay, call this as 1. See, we have sequence xn converges to a real number p. See, since alpha is mod of alpha is positive, epsilon is positive, epsilon divided by mod of alpha is also positive. So for this positive real number, there exists a natural number n naught such that mod of xn minus p is less than epsilon by mod of alpha for all n greater equal n naught. So from 1 we can write mod of alpha xn minus alpha p is less than mod of alpha into epsilon by mod of alpha, and note that this is true for all n greater equal n naught, and therefore alpha into xn minus alpha into p is less than epsilon for all n greater equal n naught, and hence the sequence alpha into xn converges to alpha into p. Okay. Means this result is also true for alpha non-zero. Okay. Means we proved that if we have a sequence xn, convergence sequence xn converges to p, and alpha is any real number, then the scalar multiplication of alpha and xn converges to a multiplication of alpha and p. Next result. let xn and yn be sequences of convergent convergent sequences of real numbers converge to p and q respectively. Then the subtraction of sequences x and yn is a sequence xn minus sequence yn, and it is a sequence whose nth term is sequence xn minus yn, and this sequence converges to p minus q. So using previous, by combining previous two theorems, we can prove easily, because xn minus yn is nothing but a subtraction of sequences xn into converges to minus 1 into q, that is minus q. Therefore the sequence xn plus minus 1 into minus 1 converges to p plus minus q, that is p minus q, and hence sequence xn minus yn converges to p minus q. This is just consequences of previous two theorems. Let xn and yn be convergent sequences of real numbers converge to p and q respectively. Then multiplication of sequence xn and yn is a sequence whose nth term is xn into yn, and we can note that it converges to p into q. Let's see its proof. Given sequences xn and yn converge to real numbers p and q respectively, and we claim that sequence xn into yn converges to p into q. Okay. Let epsilon greater than 0 be any given positive real number. To prove the claim, we have to find a natural number n naught such that mod of xn into yn minus p into q is less than epsilon for all n greater equal n naught. Okay. Let's see one adjustment. Consider xn into yn minus p into q. We can write this term as xn into yn minus xn into q plus xn into q minus p into q. I have added and subtracted a term xn into q, so its value remains same. Okay. From first two terms, take xn common. We will get xn into yn minus q. And from third and fourth term, take q common. We will get q into xn minus p. By triangle inequality, we can write right hand side is less than or equal to mod of xn into yn minus p q plus mod of q into xn minus p. Note that this is true for any natural number n. Means now we have mod of xn into yn minus p into q is less equal mod of these two terms. Okay, but mod of xn into mod of yn minus q is equal to, this term is equal to mod of xn into mod of yn minus q, and this term is equal to mod of q into mod of xn minus p. Okay, means we have this term is addition of these two terms is greater equal xn into yn minus p into q, and this is true for any natural number n. Call this as 1. Okay, see we have xn is convergent sequence of real numbers, therefore the sequence xn is bounded, and since it is bounded, there exists a positive real number m such that mod of xn is less than m for all n belongs to n. Okay. Take m dash is equal to maximum of m and this mod of q. Note that this is positive since m is positive, and we have we are taking m dash is maximum along m and mod of q, so m dash is positive real number. Okay, therefore from 1 we can write mod of xn into yn minus p into q is less than or equal to is less than or equal to, see you can note that m dash is greater equal m and greater equal mod of q, therefore from 1 we can write mod of x and yn minus pq less than or equal to m dash into mod of yn minus q plus m dash into mod of xn minus p. This is true for all n greater equal, for all natural number n. Okay. Now call this as 2. We have sequence yn converges to q. Therefore, for see alpha is positive, m dash is positive, so their division is also positive. For epsilon by m dash greater than 0, there exists a natural number n1 such that mod of yn minus q is less than epsilon by m dash for all n greater equal n. Similarly, we also have sequence xn converges to a real number p. Therefore, again, for epsilon by m dash greater than 0, there exists a natural number n2 such that mod of xn minus p is less than epsilon by m dash for all. Sorry, there should be n greater equal n1. Okay. Since xn converges to p, for epsilon by m dash greater than 0, there exists a natural number n2 such that mod of xn minus p is less than epsilon by n dash for all n greater equal n2. Now we take n naught is equal to maximum among n1 and n2. Since n1 n2 are natural numbers, their maximum is also a natural number. Okay. So if n is greater equal n naught, then we can note that n is greater equal n1 as well as n2. Since we are taking n naught is maximum along n1 and n2. Okay. It implies, but for n greater equal n1, mod of yn minus q is less than epsilon by m dash, and for n greater equal n2, mod of xn minus p is less than epsilon by m dash. From 2, if n greater equal n naught, we can write left hand side of 2 xn into yn minus p into q is strictly less than m dash into epsilon by m dash plus m dash into epsilon by m dash. Yeah. So here we have to do one adjustment again. So we can take this epsilon by, instead of epsilon by m dash, we can take here epsilon by 2 m dash. Okay. We can take this also, no problem. So 2 m dash, 2 m dash, 2 m dash, 2 m dash. Okay. So it implies mod of xn into yn minus p into q is less than epsilon by 2 plus epsilon by 2, that is equal to epsilon. Mod of xn minus yn p into q is less than epsilon. Hence, for given epsilon greater than 0, we are getting a natural number n node, such that for n greater equal n node, mod of xn into yn minus p mod of xn into yn minus p into q is less than epsilon, and therefore sequence xn into yn converges to multiplication of p and q. Okay, this is the end of the proof. Let's see another theorem. Let xn be a convergence sequence of real numbers converges to p, provided you can write with xn not equal to 0 for all n belongs to n, and p is also non-zero. Then the sequence 1 by xn means we are just taking the reciprocal of each term of the sequence xn, converges to reciprocal of p, means 1 by p. See, this is true if each xn and p non-zero. Therefore we are taking xn not equal to 0 for all n belong for each natural number n and p non-zero. Okay, proof. We have given xn a convergence sequence of real numbers converges to p with xn not equal to 0 for all n belongs to n and p not equal to 0. We claim that one by xn converges to 1 by p. Okay, means we have to find a natural number n node. Okay, let epsilon greater than 0 be any given real number. We have to find natural number n node such that mod of 1 by xn minus 1 by p is less than epsilon for all n greater equal n node. Okay, consider mod of 1 by xn minus 1 by p. By cross multiplication we can write it as p minus xn divided by xn into p, and we can write it as mod of p minus xn divided by mod of xn into mod of p, and we can write it as mod of xn minus p divided by mod of xn into mod p. And note that this is true for each natural number n. call this as 1. Okay. See, we have p is non-zero, therefore mod of p is also mod of p is greater than 0, and therefore mod of p by 2 is greater than 0, right? And we have xn is a convergent sequence of real numbers converges to p. Therefore, for mod p by 2 greater than 0, there exists a natural number n1 such that mod of xn minus p is less than mod of p by 2 for all n greater equal n1. Okay. So therefore, we can write this term as mod of p by 2 is less than minus of mod of p by 2 less than xn minus p less than mod of p by 2 for all n greater equal n1. Okay. Yeah. Okay. We will do another adjustment. Okay. See, we know that mod of xn, we know mod of a minus mod of b is always less than or equal to mod of a minus b. This is true for any two real numbers. Therefore, we can write left hand side of this term as mod of xn minus mod of p is less equal mod of xn minus p, but mod of xn minus p is less than mod of p by 2 for all n greater equal n1. Therefore, we can write mod of xn minus p mod of p is less than mod of p by 2 for all n greater equal n1. But we know that mod of a is always less equal mod a for all a belongs to R. Therefore, we can write left hand side as mod of xn minus mod of p is less than mod of p by 2 for all n greater equal n1. And therefore, we can write mod of xn is less than, add my mod of in both sides will get 3 into mod p by 2 n greater equal n1. Since xn non-zero, so mod of xn greater than 0, p is non-zero, mod p greater than 0, mod of x means both sides are positive. By taking the reciprocals, we'll get mod of Note that here we are not getting what we want. Actually, what I want, this 1 by mod of xn is less than or equal to something, right? So don't consider this. See, observe this term, right? See, from this we can write, see, I'm writing again. See, we have mod of xn minus p is less than mod of p by 2 for all n greater equal n1. From this, we can write multiply both sides by minus 1. We can write mod of minus p by 2 is less than mod of xn minus p, but this is also true for all n greater equal n1, but you can say that mod of a minus of xn minus p is less equal mod of xn minus mod p. Therefore, we can write minus of mod p by 2 is less than mod of xn minus mod p for all n greater equal n1, and therefore we can write it as mod p minus mod p by 2 less than mod of xn. Now it is correct, n greater equal n1, and therefore left hand side we can write mod p by 2, subtraction of mod p and mod p by 2 is mod p by 2 is less than mod of xn for all n greater equal n1. And since mod p by 2 and mod xn are positive, we can write it as mod of 1 by xn is less than 2 by Maya mod p n greater equal n1. Okay. Therefore, from 1 we can write one by mod of 1 by xn minus 1 by p is strictly less than 2 by mod p square into mod of xn minus p, and here it is true for n greater equal n1. Call this as 2. Yes, 1 is true for any natural number n, but 1 by mod of xn less than 2 by mod p true for n greater equal n1. So this is true for n greater equal n1. Now see, 2 by mod p square is positive, epsilon is positive, therefore for see, we have sequence xn converges to p, therefore for epsilon into mod p square by 2 greater than 0, there exists a natural number n2 such that mod of xn minus p is less than epsilon into mod p square by 2 for all n greater equal n2. Yes. Now take n naught is equal to maximum among n1 and n2. Note that it is a natural number. Yes. Therefore, if n greater equal n naught, then n is greater equal n1, as well as n greater equal n2. It implies by combining these two, we can write it is mod of 1 by xn minus mod of 1 by p is less than, since both since n is greater equal n1 as well as n2, we can write this term is less than 2 by mod p square into epsilon into mod p square by 2. See, mod p square cancel, 2 will cancel and remains, it implies 1 by xn minus 1 by p is less than epsilon. Yes. Therefore, we got for any given epsilon greater than 0, there exists a natural number n naught. There exists a natural number n naught such that 1 by xn minus 1 by p is less than epsilon for all n greater equal n naught, and hence the sequence 1 by xn converges to 1 by p. This is the end of the proof. Now, let's see the last result of this video. Let xn and yn be convergent sequences of real numbers converge to real numbers p and q respectively with yn not equal to 0 for all n belongs to n and q is also non-zero. Then the quotient of xn and yn is a sequence whose nth term is xn by yn, and we can note that it converges to p by q. It's proof it easily using previous two results, because sequence xn by yn is nothing but a quotient of sequences xn and sequence y, right? We can write this as multiplication of sequence xn and sequence 1 by yn, but we have xn converges to p, and in the last result we have proved that 1 by yn converges to 1 by q, right? Means we have xn converges to P and sequence 1 by yn converges to 1 by q by previous result. Therefore, multiplication of sequences xn and 1 by yn converges to p into 1 by q, that is equal to p into q, sorry, p into 1 by q, and hence sequence xn by yn, sequence xn by yn converges to p by q. Okay. Means in this video we have seen algebra of convergent sequences. Means if given sequences x and y and converges, then to which real number their addition, subtraction, multiplication, division converges. Okay, I'm stopping the video. Thanks for watching.